Okay, number one, from the question, we asked to analyze the possible cause for the discrepancy between the theoretical value and the measured result. Because when using a pH meter, the measured pH of HCl solution is 2.15. Okay, to answer the question, first, let's perform the theoretical pH calculation. HCl is a strong acid, so it's assumed to ionize completely. HCl become H plus Cl mean. We know from the question concentration of H plus is 0.01 m or molar. Therefore, concentration H plus equal to 10 times 10 mean squared m. pH equal to mean log 1 times 10 mean squared, and the result is 2. It was found that the theoretical pH calculation result was 2, while the measure result was 2.15, which means that the measured H plus ion concentration was lower than 0.01 m. Let's assign the possible cause. This can be caused by several factors. 1. Inaccurate pH meter calibration. If the pH meter not calibration correctly before use, the reading may be inaccurate. 2. Contamination of the solution or equipment. The presence of impurities or other substance in the measuring cup, pipette, or HCl solution can affect the actual number of H plus ion. 3. Environmental temperature. pH depends on the temperature. And the last, effect of ion activity. Okay, number 2. From the question asked, can the HA solution be used as a substitute for HCl in experiment requiring similar pH condition? And answer with appropriate calculation. Okay, to answer the question, first, it can be seen from the question that HA is a weak acid with the concentration 0.1 m or molar. HCl is a strong acid with concentration 0.001 molar. Okay, HA is a weak acid. HCl is a strong acid, but from the question, both show the same color. So, their pH is the same, which means concentration H plus is the same. Therefore, concentration H plus HA equal to concentration HA HCl. Radical Ka times Ma equal to A times Ma. Next, a radical Ka times 0.1 squared equal to 1 times 10 mean cube squared. And Ka equal to 10 to the power mean 6 over 10 to the power mean 1. And the result is 10 to the power mean 5. From the result, so if the pH of the HA solution is 3, then the Ka value is 10 to the power mean 5, meaning this weak acid is strong enough to lower the pH to the same level as 0.001 mHCl. Therefore, it can be concluded that a 0.1 mHA solution can be used as a substitute for 0.001 mHCl in experiment that only requires a pH of around 3, as the calculation show that their pH value are equivalent. However, even though they have the same pH, the chemical reactivity or reaction mechanism may differ. So, HA is only suitable to replace HCl if the experiment depends solely on pH, not acid strength or type of ions. Okay, next question is number 3. From the question asked to identify if there is a conceptual error in the calculation and determine the correct pH value. Okay, first it can be seen from the question that BaOH 2 times concentration is 0.0005 m or molar. Next, BaOH 2 times is a strong base, and belongs to the group of the valent base, meaning, okay, BaOH 2 times become Ba2 plus 2OH min. Each 1 mole of BaOH2 produces 2 mole of OH min. So, it can be said the student will only consider one OH min ion are conceptually incorrect. Next, the correct pH calculation is as follows. Concentration OH min equal to 2 times 5 times 10 to the power min 4 equal to 10 min cube. POH equal to min log 10 min cube. Next, pH is 14 minus 3 and the result is 11. Okay, next question. Next question is number 4. From the question, calculate the pH of the 0.001 m BOH3 solution and conclude whatever is more acid, more neutral, or more basic than HCl solution with pH 4. Okay, it can be seen from the question that the BOH3 solution is a weak acid with concentration 0.001 molar. Ka is 10 to the power min 9 and the reference solution is HCl with a pH of 4. First, we calculate the pH of 0.001 m BOH3. Concentration H plus equal to radical Ka times Ma. Next, radical 10 to the power min 9 times 10 min cubes. Next, radical 10 to the power min 12 and the result is 10 to the power min 6. So, pH is min log 10 to the power min 6 and the result is 6. So, it can be concluded that the pH of BOH3 is 6, while the pH of HCl is 4. So, the BOH3 solution is more neutral than the HCl solution. Since pH is 6 is close to neutral, BOH3 is classified as a very weak acid, while HCl is much more acid, with a pH difference of 2 units, where the H plus concentration is 100 times higher. Okay, next question. Next question is number 5, and this is the last question for me. Okay. From the question, we asked to compare the pH of two solutions and explain how the presence of the conjugate base affects the pH of the buffer solution. It can be seen from the question that concentration of CH3COOH is 0.1 m and Ka is 10 to the power min 5. Okay, pH of CH3COOH 0.1 m solution weak acid without buffer is first concentration H plus equal to radical Ka times Ma. Next, radical 10 to the power min 5 times 10 to the power min 1. Radical 10 to the power min 6. And the result is 10 min cube. Okay. For pH is pH min log 10 min cube. And the result is 3. pH of CH3COOH buffer solution divided by CH3COONA 1 divided 1. We use the Henderson-Hasselbalch equation. So, pH is pKa plus log A min over HA. Since the ratio is 1 divided by 1, log 1 is 0 and pKa is min log Ka is min log 10 to the power min 5 is 5. Therefore, pH is 5 plus log 1 is 5. So, the pH of the 0.1 m CH3COOH solution is 3, while the pH of the CH3COOH divided by CH3COONA 1 divided by 1 solution is 5. Buffer solution have a higher pH due to the presence of the conjugate base CH3COO min from CH3COONA, which suppress the ionization of the weak acid CH3COOH through the common ion effect. As a result, the concentration H plus in the buffer solution is lower. So, its pH is higher than that of a pure weak acid solution.
From the question above, we can write the ionization reaction first from CH3COOH in water where CH3COOH aqueous is the reverse reaction CH3COO- aqueous plus H plus aqueous. Now, VCH3COOH equals 100 ml and CH3COOH equals 0.9 m. Ki equals 1 by 10 to the min power of 5. Question: pH of solution. I use the weak acid formula concentration H plus equals root Ki times m equals concentration root on times 10 to the min power 5 times 9 times 10 to the min power 1 equals to write 9 times 10 to the power min 6 equals 3 times 10 to the power of min 3m. Next, determine the pH with the equation pH close min log concentration H plus equals 3 min log 3 equals 2.552. So, the pH of the solution is 2.552. Next, from equation number 7, we can make a dissolution reaction of an HCl in water first, where an H4Cl products an H plus Aq plus Cl min Aq. Next, we make a hydrolysis reaction where an H4 plus H2O is an alternating reaction NH3 plus H3O plus. From this question, it is known that M of NH4Cl equals 0.2 m or 2 times 10 to the power of min 1, then Kb of NH3 equals 2 times 10 to the power of min 5. What is asked is that the pH is. To calculate pH, we can use the pKb formula. First, where pKb 2 times 10 to the power of min 5. So, we get 5 min log 2 or the equivalent of 4.7. Next, we can determine the pH where by using the formula pH equals 1/2 times 410 minus pKb minus log m. So, we get 1/2 times 410 minus 4.7 minus log 2 times 10 to the power of min 1. So, we get 1/2 times 10 equals 5. Then it can be called that the NH4Cl solution undergoes hydrolysis because NH4 plus ion comes from the weak base NH3, where the hydrolysis reaction produces H plus ions, which shows the solution to be acidic and have a pH of less than 7. Next, number 8. From this equation, we first write a neutralization reaction where H2CO3 plus 2 NaOH product Na2CO3 plus 2H2O. We form this reaction in means that 1 mole of H2CO3 reacts with 2 mole of NaOH. Next, we write down what is known in the question, where it is known that V of H2CO3 equals 30 ml. The concentration of H2CO3 is equals to 0.5 m. The concentration of NaOH equals 0.3 m. A equals 2 and B equals 1. To solve this problem, we use the formula V1 times A times M1 equals V2 times D times M2. V1 is 30 ml multiplied by A is 2 multiplied by M1 is 0.5 equals V2 multiplied by B is 1 M2 is 0.3. So, we get 30 ml equals V2 times 0.3. With V2, we move the side to V2 equals 30 ml divided by 0.3. So, we get the result which is 100 ml. Then the volume of NaOH 0.3 m needed to neutralize 30 ml of H2CO3 0.5 m is 100 ml. Next question, number 9. From this question, we can write the dissociation reaction of CaSO4 first, where CaSO4 is the reversible reaction Ca2 plus SO4 to main. To calculate solubility, we can use the formula, namely S equals the mass of gram per liter divided by ml grams per mole. Then we substitute simple the formula where 0.09 divided by 136.14. Then the result is 0.0227. When we can calculate KSP with the formula equation, namely KSP equals S squared, so that the KSP value is obtained equals to 0.000515, or we can simplify it to 5.15 times 10 to the power of min 4. Then the KSP value of CaSO4 is obtained at a temperature of 30 degrees Celsius, namely 5.15 times 10 to the power of min 4, which now that CaSO4 is a cell that is diffusable of dissolved in water. Next, for equation number 10 of the equation, we can make the neutralization reaction, namely H2SO4 plus 2NaOH product Na2SO4 plus 2H2O. From the equation, it is known that M of H2SO4 is 0.2 m, then M of NaOH is 0.5 m, and the volume of NaOH is 40 ml. Then, in the question, what is asked is the volume of H2SO4. To solve it, we can use the formula V1 times A times M1 equals V2 times B times M2. So we just enter the numbers carefully, then get V1 times 2 times 0.2 equals 40 ml times 1 times 0.5. So we get V1 times 0.4 m equals 20 ml times m. Then the volume of V1 is equals to 20 divided by 0.4. So the final result is 50 ml. Then the volume of H2SO4 needed to neutralize NaOH is 50 ml.
11. Students find the pH of the LOH solution is 10 plus log 5. Calculate the base strength by determining the Kb value. The solution is, first, given MLOH equals 0.01 m equals 10 to the power of minus 2 and pH equals 10 plus log 5. Asked is Kb. The answer A. Calculate pOH from pH with the formula pOH equals 14 minus pH equals 14 minus 10 plus log 5 equals 14 minus 10 log 5. So that pOH equals 4 minus log 5. Next, count concentration OH minus. With the formula pOH equals minus log concentration OH minus. 4 minus log 5 equals minus log concentration OH minus. Log concentration OH minus equals minus 4 minus log 5. Log concentration OH minus equals minus 4 plus log 5. Concentration OH minus equals 10 minus 4 plus log 5 equals 10 minus 4 multiply 10 log 5. So that concentration OH minus equals 5 multiply 10 the power of minus 4m. Next, count its Kb value with the formula concentration OH minus equals square root multiply m. 4 multiply 10 to the power of minus 4 equals square root multiply m. Next, 5 multiply 10 to the power of minus 4 to the power minus 2 equals kb multiply 10 to the power of minus 2. Next, 25 multiply 10 to the power of minus 8 divide 10 to the power minus 2 equals kb. So that kb equals 25 multiply 10 to the power of minus 2. The result is kb 2.5 multiply 10 to the power of minus 2. So, based on calculate from the given data, the solution LOH base with concentration 0.01 m and pH 10 plus log 5 show that he is language weak. This proven from Mark calculate Kb as big as 2.5 multiply 10 to the power of minus 2. Number 12, with pH 5 minus log 4 and Ka equals 10 to the power of minus 6. Prove the calculate of the H plus ion concentration of HX acid. The answer is, first, pH formula is pH equals minus log concentration H plus. Next, substitute given pH value is 5 minus log 4 equals minus log concentration H plus. For look for concentration H plus, we can change equality. This is log concentration H plus equals minus 5 minus log 4 equals minus 5 plus log 4. Next, use characteristic logarithm. Is a log b equals log b of to the power of a, and log x plus log y equals log x multiply y. Next is log concentration H plus is equal log 10 minus 5 plus log 4 equals log 4 multiply 10 minus 5. From the equation above, we get concentration H plus equals 4 multiply 10 to the power of minus 5 m. To prove, based on the given pH value 5 minus log 4, the concentration of H plus ion is 4 multiply 10 to the power of minus 5 m. Number 13. Student use 0.02 m CH3COOH with Ka equals 1.8 multiply 10 to the power of minus 5. Calculate the pH theoretically without a pH meter. The solution is given MCH3COOH equals 0.02 m equals 10 to the power of minus 2 m, and Ka equals 1.8 multiply 10 to the power of minus 5. Asked is pH. The answer, first, concentration H plus. With the formula concentration H plus equals square root Ka multiply Ma equals square root 1.8 multiply 10 to the power of minus 2 multiply 0.02. Next, equals square root 18 multiply 10 to the power of minus 2 multiply 2 multiply 10 to the power of minus 2 equals square root 56 multiply 10 to the power of minus 2, and concentration H plus equals 6 multiply 10 to the power of minus 4. So concentration of H plus is 6 multiply 10 to the power of minus 4m. Next, count pH with the formula pH equals minus log concentration H plus. pH equals minus log 6 multiply 10 to the power of minus 4. pH equals 4 minus log 6. pH equals 4 minus 0.778. So the result is pH 3.222. Next, number 14, it's known that the pH of MOH is 10 plus log 4 and Kb equals 8 multiply 10 to the power of minus 5. Determine the concentration of the MOH solution. The solution is: first, convert pH to pOH, given pH equals 10 plus log 4, pH plus pOH equals 14. So pOH equals 14 minus pH, pOH equals 14 minus 10 plus log 4, pOH equals 4 minus log 4. Next, count hydroxide ion concentration OH minus from pOH is pOH formula pOH equals minus log concentration OH minus. Next, substitute pOH value obtained is 4 minus log 4 equals minus log concentration OH minus. Log concentration OH minus equals minus 4 minus log 4. Log concentration OH minus equals minus 4 plus log 4. Next, use characteristic logarithm is log A plus log B equals log A multiply B. So log concentration OH minus equals log 10 minus 4 plus log 4. Log concentration OH minus equals log 4 multiply 10 to the power of minus 4. So concentration OH minus is 4 multiply 10 to the power of minus 4. Next, write it down. Reaction equilibrium MOH base is MOH M plus OH minus. Next, write it down. Concentration equilibrium base or KB. KB equals concentration M plus multiply concentration OH minus divide concentration MOH equals 8 multiply 10 to the power of minus 5. Next, calculate concentration MOH with the formula Kb equals concentration M plus multiply concentration OH minus divide concentration MOH. The Kb 8 multiply 10 to the power of minus 5 equals 4 multiply 10 to the power of minus 4 to the multiply 4 multiply 10 to the power of minus 4. Divide concentration MOH. Next, 8 multiply 10 to the power of minus 5 equals 16 multiply 10 to the power of minus 8. Divide concentration MOH. So concentration MOH equals 16 multiply 10 to the power of minus 8 divide 8 multiply 10 to the power of minus 5. So 2 multiply 10 to the power of minus 5 m equals 0.002 m. So concentration the beginning of MOH is 0.002 m. Next, number 15, in titration 30 milli of 0.1 m NaOH was added to 20 milli of H2SO4 to the equivalence point. Calculate the molarity of H2SO4. The solution is on the equivalent titration, amount mole equivalent so the same with amount mole equivalent base. The formula is Na multiply Ma multiply Va equals Nb multiply Mb multiply Vb. Just click Na is Villus acidity or number of H plus ions released per molecular acid. Next, mH is concentration or molarity of acid. Next, Va is volume sour. Nb is valence base or number of OH minus ions released per molecular base. And Mb is concentration or molarity of base, and Vb is volume base. For step calculation molarity H2SO4 is the first one, nose data identification is volume of NaOH is 30 milli. Concentration NaOH is 0.1 m and volume of H2SO4 is 20 milli. Next, number 2, determinant valence basic and base. To H2 so SO4 or acid sulfate is sour diprotic, which means he released 2 H plus ion per molecule. So Na is 2. Next, NaOH or sodium hydroxide is base monoprotic, which means he released 1 OH minus ion per molecule. So Na is 1. Next, to substitute mark to formula titration is Na multiply Ma multiply Va equals Nb multiply Mb multiply Vb. Na is 2, Ma is escort multiply 20 milli equals Nb is 1, Mb is 0.1 m, and Vb is 30 milli. So 40 multiply Ma equals 3. So that Ma equals 0.075. So that concluded based on calculation use formula appropriate titration molarity solution H2SO4 is 0.075 m. That means each liter of solution H2SO4 contains 0.075 mole sour sulfate. This gives description quantitative above how much concentrated solution sour the.
Well, look at the problem. From the problem, it is known HCN is a weak acid. The concentration of HCN is 1 times 10 to the power of minus 4 molar. The value of the acid ionization constant Ka is 4 times 10 to the power of minus 8. Ask, what is the pH value? Solution, ionization reaction of HCN in water. HCN in aqueous solution ionizes into H plus and Cn minus. To calculate the hydrogen ion concentration, we use the formula the concentration of H plus is equal to the square root of Ka times the molar concentration. We substitute the values. The square root of 4 times 10 to the power of minus 8 multiplied by 1 times 10 to the power of minus 4. This multiplication results in 4 times 10 to the power of minus 12. The square root of 4 times 10 to the minus 12 is 2 times 10 to the minus 6. Next, we calculate the pH. pH is equal to the negative logarithm of the hydrogen ion concentration, pH minus log 2 times 10 to the power of minus 6. By the properties of logarithm, this is equal to minus log 2 plus log 10 to the minus 6. The value of log 2 is close to 0.3 and log 10 to the minus 6 is minus 6. So, the negative of open parenthesis 0.3 minus 6 close parenthesis is the same as 6 minus 0.3. The result is 5.7. Thus, the pH value of the HCN solution is 5.7. This means that the solution is slightly acidic because the pH is still above 5, which indicates that only a few hydrogen ions are formed. This is in accordance with the nature of cyanide acid as a weak acid. In this next question, it is known LOH is a weak base. The pH value of the LOH solution is 8 plus log 6. The value of the base constant or Kb is 4.5 times 10 to the power of minus 5. Ask, what is the concentration of LOH solution? First, we convert the pH to pOH. To find pOH, we use the formula. pOH is equal to 14 minus pH. We substitute the pH into the formula, so it becomes pOH 14 minus open bracket 8 plus log 6 close bracket. Next, we describe the calculation. 14 minus 8 is 6. So we get pOH 6 minus log 6. So the final form is pOH 6 minus log 6. So the concentration of hydroxide ions is 6 times 10 to the power of minus 6 molar. This means that the concentration of a H mean ions is equal to the square root of the product of Kb and the base concentration. We substitute the numbers into the formula. 6 times to the power of minus 6 square root of 4.5 times to the minus 5 times m. The next step, we square both sides to eliminate the root. So 6 times 10 to the minus 6 squared is 36 times 10 to the minus 12. We equate this result to the 4.5 times 10 to the minus 5 times m. Next, to find m, we divide both sides by 4.5 times 10 to the minus 5. So, m is equal to 36 times 10 to the minus 12 divided by 4.5 times 10 to the minus 5. 36 divided by 4.5 is 8, and 10 to the minus 12 divided by 10. This means that the concentration of the LOH base in the solution is 8 times 10 to the power of minus 7 molar. Next, in this next question, it is known that the value of Ka is 4 times 10 to the power of minus 6, and alpha, or the degree of ionization, is 0.02. Question 1. What is the pH before adding NaA? 2. What is the effect of adding NaA? Solution. Then we substitute into the formula. Ka equals alpha squared times m. 4 times 10 to the minus 6 equals 0.02 squared times m. 0.02 squared 0.02 squared is 0.004, or 4 times 10 to the minus 4. So our equation becomes 4 times 10 to the minus 6 equal 4 times 10 to the minus 4 times m. To find m, we divide both sides by 4 times 10 to the minus 4. 4 divided by 4 is 1, and 10 to the minus 6 divided by 10 to the minus 4 is 10 to the minus 2. So we get m equals 10 to the minus 2, or 0.01 molar. So the initial concentration of HA acid is 0.01 molar. Next, we calculate the hydrogen ion concentration using the formula H plus equals alpha times m. Alpha is known to be 0.02 and m is 0.01. So we multiply 0.02 times 0.01 is 0.002, or in scientific notation 2 times 10 to the minus 4. So the concentration of H plus ion is 2 times 10 to the minus 4 molar. Now we calculate the pH value. Negative log of 2 times 10 to the minus 4. Then we break down the logarithm. Negative log 2 minus log 10 to the minus 4. Log 2 is about 0.3, and log 10 to the minus 4 is minus 4. So pH equals negative open parenthesis 0.3 minus 4 close parenthesis, which equal 4 minus 0.3. The result is pH equals 3.7. Now for the second part, NaA is the salt of HA and it dissociates into Na plus Na minus. A minus is the conjugate base of HA. Adding A minus will shift the equilibrium to the left according to Le Chatelier's principle. This reduces the hydrogen ion concentration and increases the pH. As a result, the solution becomes less acidic and acts as a buffer solution. Next, it is known. First of all, we collect all the data needed to calculate the number of moles of HCl gas that dissolve in water. The volume of HCl gas used was 24 milliliters, which when converted to liters is 0.024 liters. The pressure of the gas is 76 centimeters of mercury, which under standard conditions is approximately 1 atmosphere. The room temperature used is 27 degrees Celsius. To convert to Kelvin, we add 270 to 27, which give 300 Kelvin. The value of the gas constant R is 0.08 with unit of liters times atmosphere divided by mole times Kelvin. Finally, the volume of water where the dissolution takes place is 250 milliliters, or in liters it becomes 0.25 liters. As pH of the solution. Next, we calculate the number of moles of HCl gas using the ideal gas formula. Moles equals pressure times volume divided by R times temperature in Kelvin. We substitute all the values into the formula. 1 atmosphere times 0.024 liters divided by 0.08 times 300 Kelvin. 1 times 0.024 is 0.024, then 0.08 times 300 is 24. So we get 0.024 divided by 24, which is 0.001 moles of HCl. Next, we calculate the concentration of hydrogen ions. Concentration equals moles divided by volume of solution. So 0.001 mole divided by 0.25 liters is 4 times 10 to the power of minus 3 molar. Now we calculate the pH using the formula. pH equals negative log of the hydrogen ion concentration. So pH negative log 4 times 10 to the minus 3. First, we break down the logarithm. Log 4 times 10 to the minus 3 is log 4 plus log 10 to the minus 3. The value of log 4 is about 0.6 and log 10 to the minus 3 is minus 3. So the expression becomes negative open parenthesis 0.6 minus 3 close parenthesis. 0.6 minus 3 is minus 2.4 and the negative outside makes it to the point 4. So the pH of the solution is 2.4. That means the solution is acidic as expected from a strong acid like HCl. Next, in this last question, here is a breakdown of the calculation which is number converted into sentence. As per your request, it is known the volume of KOH solution that was titrated was 10 milliliters. The volume of HCl solution used was 18.72 milliliters, which converts to 0.0187 liters. The concentration of HCl is 0.115 molar. Question: how many moles of KOH reacted? The reaction that occurs Potassium hydroxide (KOH) reacts with hydrochloric acid HCl to form potassium chloride KCl and water H2O. Reaction equation: KOH plus HCl produce KCl and H2O. Solution step. First, we calculate the moles of HCl using the formula. Moles equals concentration times volume. The concentration of HCl is 0.115 times the volume 0.01872 liters. This multiplication yields 0.0021528 moles of HCl. Because the reaction between KOH and HCl has a 1-to-1 ratio, the numbers of moles of KOH that react it also 0.0021528 moles in 10 milliliters of solution. Next, we calculate the moles of KOH in 500 milliliters of solution. First, divide 500 milliliters by the milliliters, which is equals 50. Then multiply 50 by 0.0021528 moles. The result is 0.1064 moles of rounded to 0.108 moles. So the number of mole of KOH in 500 milliliters of solution is approximately 0.108 moles.
Okay, next question number 21. Several students conduct an experiment using litmus paper to identify the properties of substance A, B, and C. Data obtained: substance A changes red litmus to blue. Substance B does not change the color of litmus. Substance C changes blue litmus to red. Based on the data, examine the result of the experiment and explain the possible errors that can occur if the interpretation of the result is incorrect. Answer: based on the result of the experiment with litmus paper is substance A changes red litmus to blue, meaning that substance A is basic because a base changes red litmus to blue. Next, substance B does not change the color of red or blue litmus, meaning that substance B is neutral. Why? Because it does not affect the color of litmus. Next, substance C changes blue litmus to red, means that substance C is acidic. Why? Because acid changes blue litmus to red. Next, possible errors if interpretation is incorrect. 1. Misinterpreting the color change. 2. The condition of the litmus paper is not good. Next, number 3. The amount of substance is too little or too dilute. Number 4. Contamination. And number 5. Not using two types of litmus. So, interpretation of litmus test result must to be done carefully. For accurate result, it is important to use good litmus paper, test with both types of litmus, and ensure there is no contamination. Next question number 22. In the laboratory, a student observed two solutions. Solution A, H2SO4, and solution B, CH3COOH. Both appear as clear liquids and are known to contain hydrogen atoms in their chemical formulas. When tested with an indicator, solution A show a drastic change in pH, while solution B show only a small change. Based on test observation, compare why the two solutions show different behavior, even though they both contain hydrogen atoms in their molecules. Answer: the difference in behavior between solution A (H2SO4) and solution B (CH3COOH) occurs due to the difference in acid strength of each compound, even though both contain hydrogen atoms. Okay, we can see this is a comparison table. aspect, solution A and solution B. Number 1. Compound name. Solution A is sulfuric acid. Solution B is acetic acid. Number 2. Acid types. Solution A is strong acid and solution B weak acid. Number 3. Degree of ionization. Solution A almost 100% and solution B a small portion is ionized. Number 4. Acid strength. Solution A very strong, produce many H plus ions. Solution B weak, only a small portion of the molecules produce H plus ions. Number 5. pH of solution. Solution A very low and solution B relatively higher. Number 6. pH change with indicators. Solution A drastic color change and solution B slow or unnoticeable color change. Number 7. Level of electrical conductivity. Solution A high because many ions are formed. Solution B low to medium because few ions are formed. Although both contains hydrogen atoms, H2SO4 is a strong acid that completely ionizes in water, while CH3COOH is a weak acid that only slightly ionizes. Next, question number 23. A student is doing a titration experiment in a school laboratory. He takes 20 ml of sulfuric acid solution or H2SO4 of unknown concentration. The drops 0.1 mol sodium hydroxide or NHOH solution from the burette into the acid solution. After several drops, the indicator shows that the equivalence point has been reached when the volume of NHOH used reaches 30 ml. Prove the molarity of the sulfuric acid solution used by the student based on the titration data above. Answer. Step 1. Write the reaction equation. H2SO4 aqueous plus 2NHOH aqueous becomes Na2SO4 aqueous plus 2H2O liquid. Next, step number 2 given. 1. Volume of H2SO4 is 20 ml or 0,020 liter. Number 2. Volume of NHOH is 30 ml or 0,30 liter. 3. Molarity of NHOH is 0,1 mol and molarity of H2SO4 unknown or N. Next, step number 3 is calculate the moles of NHOH used. Mol NHOH equality M times V equality 0,1 mol divided by 1 times 0,30 liter equality 0,03 mol. Next, step number 4. Use the mole ratio according to the reaction equation. Moles H2SO4 equality 1/2 times mol NHOH equality 1/2 times 0,003 equality 0,0015 mol. Okay, the last step. Calculate the molarity of H2SO4 M equality moles divided by volume or L equality 0,0015 divided by 0,020 equality 0,075 mol divided by liter. Next question number 24. In a lab, Edo mixed a carbonic acid solution or H2CO3 into water. After a few minutes, he measured the pH of the solution and was surprised because the pH did not change drastically like when he mixed HCl into the water in the previous experiment. Edo then concluded that H2CO3 is not an acid because it does not make the solution very acidic. Based on this situation, conclude whether Edo's statement is true or false. Why the pH of the H2CO3 solution does not change drastically like a strong acid. Answer: Edo's statement is wrong. Why? Edo's statement is wrong because although the pH of the H2CO3 solution does not drop drastically like when mixing HCl, this does not mean that H2CO3 is not an acid. H2CO3 is still classified as an acid, but it is included in the category of weak acid. This means that H2CO3 does not undergo complete ionization in water. When HCl, or a strong acid, is dissolved in water, almost all of its molecules are ionized and release H plus ions or protons, causing a sharp decrease in pH. Meanwhile, only a small portion of H2CO3 is ionized. So, even though it does not decrease the pH drastically, H2CO3 is still classified as an acid. It is just weak in terms of ionization. Okay, the last question. A student conduct an experiment by dissolving a small amount of potassium hydroxide or KOH into water until the solution volume reached 10 liters. He noted that the amount of KOH used was 0.001 mole. Without using a pH meter, the student stated that the solution must have a pH close to neutral because the amount of base added was very small compared to its volume. Prove whether the student's statement is correct or not by calculating the pH of the solution based on the number of moles of KOH and its volume. Answer: it is known moles of KOH is 0.001 mole. Volume of solution is 10 liter. KOA is a strong base, so it is completely ionized. And equality N divided by V. Equality 0,001 divided by 10. Equality 0,0001. Next, concentration OH power minus equality 10 power minus 4. Next, POH equality minus log 10 power minus 4. Next, POH equality 4. Next, pH equality 14 minus POH. pH equality 15 minus 4. And the result is 10. So, the pH of the solution is 10